So we're going to do a real quick run through quantum theory and the atom and how we came up with the quantum model of the atom. So as electrons move from higher energy to lower energy orbits, they emit energy. That's where we get our atomic emission spectrum. They're emitting energy. This Bohr was the first person who quantified the release of energy with hydrogen, but his model of very discrete circular orbits that you guys have seen before doesn't work for any element other than hydrogen, which is the one he used to develop it. So Bohr was born in Denmark, and he lived from 1885 to 1962. And this is what his model looks like. He says that an atom that is in its ground state, its electron is in one specific circular orbit. Then it gets excited, and that electron moves to a bigger orbit, which is more energetic than being in that lower state. As it moves back to the lower state, it emits some form of light, depending on which orbit it bounces back from. And so he had the Balmer series, which is your visible light that they emit. There's an ultraviolet light and an infrared light. And he said that this comes from discrete circular orbits, that an atom is flat like a plate. And then n equals the quantum number of energy levels in this image. And then the lines, the purple red lines, and then the colored lines, those represent the movements caused by atomic emissions. Louis de Broglie, who was born in France and lived from 1982 to 1987, actually helped create the quantum mechanical model of the atom. He proposed that if waves can behave like particles, maybe particles can behave like waves. And so he came up with an equation that represented that, and that's called the de Broglie equation. And it is lambda equals Planck's constant divided by the mass times the velocity or speed of an electron. And this is it broken down. Okay, this equation represents the wave nature of particles. So if you remember, we looked at the particle nature of waves in an earlier lesson. So this is the wave nature of particles. It's adding wavelength with mass and speed instead of energy with frequency. And again, we're using Planck's constant because there's that distinct amount of energy, right? That it cannot increase or decrease by anything other than that. Erwin Schrödinger, which we've also seen before, treated electrons as waves, and he built on de Broglie's equation and refined the quantum mechanical model to what we use now. Schrödinger's equation is a lot more complicated, and we don't need to know it to just understand what he's doing. So Schrödinger's model applied equally well to elements other than hydrogen. It wasn't just hydrogen that this worked for. It works for everything, which is why we still use it. And this is what the quantum mechanical model actually represents. So the wave function predicts a 3D region around the nucleus, and this is what's called the atomic orbital. In this particular map, you can see that there's regions of density where the more dots you see, the more likely you're going to find the electron there around the nucleus. And then you just create a boundary. And then you just create a boundary where that probability gets below a certain threshold, and then that's what we call an orbital. Werner Heisenberg, born in Germany, and I did misspell his name in the notes, so if you could fix that, it should be B-E-R-G, not B-U-R-G. He showed that it was impossible to take a measurement without disturbing an object in some way. And so what he said was he created the Heisenberg uncertainty principle. It says it's impossible to know precisely both velocity and position of a particle at the same time. Remember this one. It's another one of those principles you should know word for word. And it's the basis for that cloud model that Schrodinger created. So his theory was if you measured something like a particle, you're hitting it with some sort of energy. So you'll either change its path or velocity, like a cue ball smacking into another pool ball. All right, that's it. I'll see you in the next lesson.